Welcome to the next lesson in Math 8. This is Unit 5, Lesson 12. How much will fit? We're going to reason about the volume of different shapes, and we're going to do that by actually analyzing some different containers and some different pictures. The first one that I have for you is actually a container that holds 200 beans. Let's see if I can figure out where I put it. That's not it. There it is. So the little container there on the left holds 200 beans. What would be your estimate for how many beans are in the larger jar? All right, now that you've entered that in there, this little container, you might estimate that that's maybe like a quarter or a fifth of what we have right here. So if there's 200 beans here, there's 4 times as many or possibly 5 times as many. What I noticed is that the opening here at the top, if this was a rounded container, we could call it the diameter. The diameter is not quite as large as the diameter of this first one, or the larger jar of beans. So I mean, we could look at the two and we could say, you know, maybe the estimate is somewhere between 800 and 1,000 beans. Okay, let's look at the next one. Here we have 3 boxes. We've got a box of pudding, a box of pasta, and a box of rice. So these are all rectangular prisms. The pasta box right here in the middle, the pasta box here in the middle holds 8 cups of rice. How much rice would you need for the other rectangular prisms? All right, so the question then would be, how does this smaller box compare to the larger box? Probably on average with it. What we can look at is we look at all these different edges and we figure out, you know, this edge right here is probably about half the width of the edge of this one, and the height is probably about half the height. So it would take about 4 of those to fill up the bottom half, and probably 4 to fill up the top half, so probably 8 times less in this smaller pudding box. So about, I'd say 1/8 of 8, so maybe a cup of rice. And then as I look at this other chicken stock, I would look at the sides and I see they're probably about the same width, and the height is probably about the same, but this dimension here across the front doesn't appear to be quite as long. I'd say it's maybe like 3/4 that length. And so I would estimate about 3/4 of a cup, or 3/4 of 8. So probably about 6 cups of rice in here compared to this one here. Next picture is talking about 3 of these cans. This is a can of pumpkin, obviously the one that says pumpkin. Fun fact, did you know that in Moses Lake, we grow a lot of organic pumpkins, and this is where a lot of them end up, in cans like this. When we talk about these cans and these cylinders, we're talking about the smallest can, or excuse me, this pumpkin can holds 15 fluid ounces of rice. So 15 fluid ounces, and how would that compare to the other cylinders? Approximately how much do you think needs to go into the rolled oats versus the tuna? All right, when we look at these, it appears, if I could take this can and put it right on top of the tuna can appears to have approximately the same diameter. And we look at the height of it is approximately here on the can. I would say it's probably about 1/3 of the size of the pumpkin. And so with the pumpkin, I would be estimating about 5 ounces into the albacore, into the tuna. And then if I'm going into the rolled oats, I think that the diameter is just a little bit larger, not a lot, but I definitely know it's taller. I'm going to estimate probably about twice as much, or twice as many ounces into the rolled oats as into the pumpkin, if not 3 times as many. So somewhere between 30 and 40 ounces in there. Next one is 2 cones. These are my favorite kind of cones. The question is, this small cone holds 2 ounces of rice. How many ounces would the larger cone hold? Alrighty, so when we're looking at this, maybe your question was, well, do I fill in this top edge? Yeah, we would say considering filling this all the way to the top. I think the cone is one of the harder ones to estimate, just simply because there's a lot of round sides to it. And so knowing the exact volume of a cone will be something that would be really helpful. So I would say like this cone to this cone, I'd be willing to estimate the smaller cone at approximately 1/3 of the larger cone, and say this larger one probably holds 6 cups of rice, between 5 and 6 cups. Final figure, we got a golf ball and a baseball right next to each other. And the golf ball, if it were hollow, it would hold about 2/10 of a cup of water. If the baseball were hollow, how much would that one hold? Alrighty. With this one is also really deceiving because we have to look at that piece, and not only is it really small and it's hard to fit it in to where it's at, or fit it into the shape of the baseball or the space of the baseball, it's really hard to make that estimate. For me, I made that estimate at about 5 times more, and I would think somewhere between 4 and 5 times more. So between 8/10 of a cup and 1 cup of water inside of it. Right. So we just answered all these questions, and we're on to the last part. It says, what shapes are the faces of each type of object shown here? For example, all 6 faces are of a cube or square. So when we're talking about the shapes, we're talking about these shapes here on the next page, on page 2. It says, what shapes are the faces of each type of object shown here? In part A, this is that Jello box. When we look at the faces on this, we're talking about each of these side faces like this. And so we say, what are the faces for the object shown? This one, all 6 faces are rectangles. All right. What about the cone? How would you describe that one? Well, the bottom face is definitely a circle. So it's a circular shape. What about around the top part up here? How would we describe that one? Well, that face right there, since it's rounded, we have a hard time calling that a face, because what it does is it wraps around the figure. If I were going to take that piece and actually cut it off, so if I could take just this piece right here, cut along this line right here, what I would see is if I unwrapped that cone, I would see a rhombus. It'd actually be more like not necessarily a rhombus. It would be kind of a figure that looks like this. Kind of like a pie plate-ish thing, or a quarter circle, or something like that. That's the kind of shape. So how would you describe that? Around a triangle or something? And for that reason, we really don't necessarily call this a face because it's rounded, but we would recognize something like that. On a pasta can, or this pumpkin can, we have 2 faces. I guess I want to make it really clear. This side, this whole section right here on a cone is not actually a face, and it's for the reason that it's arched and rounded all the way around. So on the pumpkin, we have 2 faces that are circular, and then this piece that goes around the middle is not really a face. It's again, for the same reason, it's rounded, it's circular. If I could cut it off and lay it out flat, it would be rectangular. And then for D, for a sphere, there are no faces. It can come with half circles, half prisms, so on and so forth. So when we talk about these, this is a super important piece when we talk about what a face has to be. A face has to be a flat side, a flat plane that can fit against another flat plane. And so when understanding that these faces could be referred to as a base, it helps us to understand how to use the formulas that come with these, because all of these have a base times a height, a base times a height, a base times a height. But this one with the sphere, there's no such thing as a base in its formula. Okay, so we'll have a base times height, base times height, base times height. But the question that comes down to is this. When we're talking about base in this case, base is equal to a big capital B, which means that there's going to be more information contained inside of here. So we have base with a little b. This is just a linear measure. This is a product of measures. Okay, just want to make sure that we understand that before we move on any further. So there's a big B base and a little b base, and we have to understand the difference between both. So which faces could be referred to as the base of an object? Well, if it's rectangular, we could have that one. If it's the bottom as a circle, we could do that one. So we could have the faces that can be referred to as a base, A. All of those ones could be bases. And B, just the circular part, the circular bottom. And then C, top and bottom. Okay. So pay attention to those pieces. D, no base. All right. Final part of this. Here's a method for quickly sketching a cylinder. Draw two ovals, connect the edges, and which part of your drawing would be hidden behind the cylinder? Make sure these parts are dashed lines. So when we're talking about this, here's your first circle, your bottom circle right up here. So we want to do something like this. Draw a cylinder, and then an oval and an oval. Draw the edges, and then what they're saying is the part that's hidden, they're saying that we should take this part right here and just make a dashed line, because then it's the hidden. Wow, that was terrible. I didn't move it up. Sorry. Do this again. Oval, oval. It'd be nice if they were the same size. And then draw your sides. And then across the bottom, take that little line that you made of that oval and just make it into a dashed line. That way we can hide it a little bit better. And then include a short, tall, narrow, wide, sideways. Go ahead and just play with it. Label the radius. Radius, remember, is from the center of the circle out, R. And then the height would be from either radius to radius. This could be the height, or this edge right here could also be the height. So go ahead and practice that a couple times. And then move on. There's one more fun question that I want you to go ahead and give a try. A soccer ball is a polyhedron with 12 black pentagon faces and 20 hexagonal faces. How many edges in total are in this polyhedron? So everywhere along here, even though a soccer ball looks like a ball, it's a polyhedron. It's actually not technically a ball. It's the air that pushes it out, or a sphere. So when we're talking about edges, how many of these edges are there? So go ahead and give it a roll, see what you can come up with. The basis of this lesson is this. The volume of three-dimensional figures, like a jar or a room, is the amount of space the shape encloses. So how much can you put in it? Like the beans and the pasta and the pumpkin and the rice, all those other things that we put into them. We might say that a room has 1,000 cubic or holds 1,000 cubic feet, or that a pitcher carries 5 gallons of water. All of these pieces are normal everyday things that we do. In earlier grades, we talked about three-dimensional figures with flat faces that are polygons. We learned how to calculate the volume of rectangular prisms. And here we found out that volume is the length times the width times the height. Now we're going to study these other three figures, cones, cylinders, and spheres, and we're going to figure out just what we mean by the volume inside of those shapes. My favorite volume is the cone because of the ice cream. To help us to see these shapes better, we can use dotted lines to represent parts that we couldn't actually see in the solid. So what you'll notice on your paper is this is a little stippled line or a little bunch of dots to tell that it's much lighter, and it gives some dimension for us to be able to actually look at that object. Final thoughts. The objects that we're after, we could really find the volume of anything. And what objects could the other figures in the picture represent? These things represent a lot of different things in life. So think about it. Have a little fun today. I hope you have a great day today.